so thank you for my second talk. Yesterday I was sitting, today I stand, and all goes well, tomorrow I'll fly. So last talk we talked about this category, definable analytic spaces, which is supposed to have sort of all the benefits of algebra analysis in some sense. And today we're going to apply that to period images, studying images of period maps for variations of Hodge structures. Let me start by just motivating that, because not everyone maybe is familiar with this kind of thing. So what is the motivation? And the motivation basically is we want to say something about moduli spaces, but moduli spaces are hard. I don't study them, so I don't know exactly how hard they are, but people who study them assure me they are hard. And the idea is that we want to extract some kind of information in order that's more easily manipulable. And we're going to do that using cohomology. It's going to give us sort of these somewhat complicated linear objects with which to study moduli. And things are actually pretty good. Often, like in some cases that I mentioned here, we have Torelli theorems that tell us that, in fact, we can fully determine the moduli space, the parameter space of a class of varieties using this cohomological data. So I have some examples here. The classic one from which it gets its name, Torelli, is curves. If you look at hyperbolic curves, they're fully classified by their cohomology, the way we'll review. And there's various higher dimensional examples. There's abelian varieties, K3 surfaces, more general classes of labials, and there's often subtleties, but that's kind of the general gist of the picture. Okay, so to review, let's go over what a Hodge structure is, sort of the basic object we're going to use today to study varieties. So given the variety, the idea behind the Hodge structure is you sort of have two different types of cohomology and a transcendental isomorphism between them. You have sort of ordinary singular cohomology. Oh, and we're only going to talk about smooth projective varieties. There's a more complicated picture in general, but that doesn't carry any additional weight for us. So we have sort of ordinary cohomology. And on the other hand, we have de Rham cohomology, which admits a Dolbeault decomposition. You can think of this concretely as de Rham cohomology, sort of closed forms, mod exact forms. You have a holomorphic structure, so you can talk about closed PQ forms for any P's and Q's. And if you're algebraic, more than the Kähler, then you have a decomposition like this. And so the structures we'll record are the integral Vedic cohomology. That's got an ordinary sort of cup product on it. You can take two classes, intersect them, couple with some appropriate power of your O1 class, your projective class, and you could end up in top cohomology that gives you a number. So you get this bilinear form. And then if you tensor with C, you have this decomposition into complex subspaces. And so given how that's the basic sort of set of structures we want to study, we're going to abstract it out to, we're not going to, but Hodge theory abstracts it out in the following way, where you just consider a free abelian group, L, called the lattice, take a bilinear form on L that's either symmetric or anti-symmetric, depending on your weight. And then when you tensor with C, you get this kind of decomposition. So one thing, if you haven't seen this before, one thing that's, I think, helpful to keep track of is you only keep track of the abelian group with a bilinear form, or you only keep track of the complex decomposition. Neither of those have moduli. There's sort of only one isomorphism class of those types of objects. Where you really get the moduli is by fixing an isomorphism, taking your lattice and putting it inside your complex vector space. We'll see a concrete example of that soon. And then just like what's true in the smooth projective case, we're going to abstract that out to the general case. So your HPQ group satisfies this conjugacy assumption. Importantly, they have this isotropicity condition. If you pair together a PQ form and a P prime Q prime form, it's only non-zero if they're conjugate to each other. And then you have this positivity condition that if you work by either the P minus Q, then this Q form is positive on the LPQ piece. So you get sort of this orthogonal decomposition. One thing it's really confused me for a long time in Hodge theory when I first learned it, because we don't explain that keeping track of the HPQs, and that's because in families, the HPQs don't vary holomorphically. They can't because they're complex conjugate to each other, right? So that's one way of knowing that, there's no way they can vary holomorphically. So instead, what we do is use filtrations, which is another way to factor the same information. It's a little less convenient, but it does vary holomorphically, where you just direct sum all of these LA pieces in some way, and then you can rephrase the conditions in this way. And you can recover the LPQ pieces from the filtered pieces and their conjugate. So this is all just some sort of, somewhat tricky, but linear algebra, which you can safely ignore if it's new. As a simple example to see how Hodge theory can record sort of actually a lot of information about your variety, go over this classic example where you can actually recover an elliptic curve, complex elliptic curve, entirely from its Hodge structure. So see how that works. You take an elliptic curve over C, then you have uniformization, which tells you that the elliptic curve can be written as the complex numbers modulo some lattice. In terms of the basis tau 1, tau 2 for that lattice, you can then record the H1 as just the dual basis. And now how does the transcendental de Rham isomorphism works? Well, you take a form and you integrate it along cycles. That's how you get a cohomology class. The filtration comes from just the H naught omega 1 piece, and the elliptic curves have one differential form up to scale. It's just induced from Z. So dz, if you integrate it along tau 1, you get tau 1, along tau 2, you get tau 2, so it maps to this class here. And then if you just write down this purely Hodge theoretic notion, where you're just using the Hodge theory, the filtration here on the lattice, then you recover your elliptic curve. Go over there. So for elliptic curve, this is a concrete way to see that the Hodge theory fully records the modular. And so this gives you the sort of somewhat classical fact in this language that if you look at the modular space of C elliptic curves, it's the same as looking at the modular space of Hodge structures of weight 1 and rank. Okay, so what's the goal for us? Well, we're looking for some sort of way to construct moduli. We're assigning a Hodge structure to every single variety. So the goal is to construct some sort of moduli space of Hodge structures. And you can do this in a fairly sort of concrete way because the data is just linear algebraic. And the first thing that you do is you just look at the space of filtration. So we'll let G be the automorphism group of our polarized lattice. The polarization refers to this. This is just bilinear form Q here. So we're just looking at filtration satisfying the sort of isotropicity condition. And that turns out to be some sort of flag variety. You can write it concretely as the complex points of your group modulo some parabolic group. And then inside there, the positivity condition on Q cuts out some open domain inside of your algebraic variety, D, just imposing the positivity of this form here on the LPQ pieces. And this D is also symmetric in this way. It's acted on only by the real points now because the complex points don't play well with this group. And it's isomorphic to GR mod M, which might look familiar from Hermitian symmetric spaces. The difference here, though, is this M might not be a maximal compact subgroup, it's just a compact subgroup. And G of Z mod D is in some precise sense the moduli space. There's some orbifold points, which we ignore, but every Hodge structure occurs, every complex Hodge structure of this sort of type, where you fix these Hodge numbers and this lattice of this form, occurs at a single point in this moduli space. And yeah, you can show it's not hard that GZ acts sort of nicely on D, so the quotient becomes an analytic orbifold. In fact, that will ignore the orbifold structure and just treat it like a regular space. Okay, so very concretely, let's just work things out for elliptic curves because it's more familiar in that setting. In that case, we're looking at rank 2. I should have written this down here. I apologize. A rank 2 guys of weight 1 with Hodge numbers 1, 1. So your G becomes SL2. Your space T check just becomes the projective line. And, not surprisingly, your D just becomes the upper half plane inside the projective line. That's what you get with the positivity condition. In this case, your M is maximal compact. It's just SO2. And you get the usual parameter space H mod SO to Z, which you can think of as lattices up to scale. And in this case, this has a natural algebraic structure on it. The familiar J function gives you a rational coordinate on the space. So this does end up being algebraic as a complex space. So very briefly, if you do this for abelian varieties, you get a very similar picture. Everything's the same as elliptic curves. The dimension is now higher. So instead of looking at lines in two-dimensional space, you're looking at Lagrangians inside C to the 2G, equipped with some symplectic pairing. And then if you cut out the positivity condition, you get the Siegel symmetric space, which is a generalization of the usual upper half plane. And this quotient gives you the moduli space of principally polarized abelian varieties. This has an algebraic structure, but it's substantially more complicated. Not rational. Usually it eventually becomes general type. So There's nothing super simple one can say about it. And those are nice cases, but sort of part of the thrust of the talk today is that most period domains do not admit an algebraic structure. This is a result due to Griffiths, Robles, and Toledo in the general case. They actually show that the only ones that admit an algebraic structure are basically coming from Shimura varieties and projective spaces, sort of Grassmannians, in a very concrete sense. The simplest example to keep in mind of a space that's still small enough you can sort of hold it in your head, but it's not algebraic, is, in my opinion, the space of weight 3, where all the Hodge numbers are 1. So this is a 4-dimensional complex space. I want to go over just not quite the proof, but the thrust of how you can tell these spaces aren't algebraic, because it's very concrete. So this M, if you remember, is non-maximal. It's the real part, the real stabilizer of your Hodge structure. But it sits inside a natural maximal group K, which just preserves, ignores basically your filtration, just cares about the even and odd pieces. Familiar with the Hodge metric, which is the stabilizer of the Hodge metric, so it's a unitary group. But regardless, if you look at this G mod M to G mod K, you get holomorphic fibers. Do you? Even though the space G mod K is typically not holomorphic, and this map is therefore not holomorphic, the fibers are still holomorphic. And concretely, if you look at the case up here of Hodge numbers 1, 1, 1, 1, your stabilizers become U1 cross U1 is M, and K becomes all of U2. So the real difference is dimension 2. So if you were complex, the dimension had to be 1. And yes, in fact, these curves turn out to be just a family of P1s. Okay, so having a bunch of P1s doesn't prohibit you from being algebraic, but it turns out we have way too many P1s. So because we have this action by G, for any complex G, you can act on Z sub U, and you will in general get more compact fibers. If you're in the special case of being a Shimura variety or something very close to it, then you will not. You will just get this family, but in general, you get more compact fibers. And you might notice that I'm cheating a bit because GC doesn't act on D, only acts on D check. Because we're dealing with compact fibers, if you act by a small enough element of GC, something close to 1, you will stay within D. This is in fact a legal thing to do. And so Griffiths, Robles, and Toledo study this action, and they in fact show that there's a lot of these P1s, enough to make your space rationally connected. Every pair of points is connected by some chain of P1s. Okay, so that's still not quite enough to show the not algebraic, but the nail in the coffin is that the fundamental group, this should be a pi 1, sorry. The fundamental group of D mod GZ is just GZ up to some stabilizer nonsense. So in particular, it's infinite, which means now that it can't be algebraic. You can't have an infinite fundamental group and be rationally connected by a theorem of Kolar. Okay, so in general, you're not algebraic, but you always contain a lot of algebraic varieties. So where do these occur? Well, if you have any smooth projective family, X over S, fix some small enough dimension, then you, for every single point, can just look at the fiber and take the cohomology of that fiber. You got to take the primitive cohomology, which I'm not going to talk about, but it's not a big deal. That gives you a Hodge structure, and so you get this period map from S to D mod GZ, and you can show that this period map is holomorphic. In fact, something I won't talk about, but it's very important, is these period maps aren't just holomorphic, they in fact satisfy a differential condition known as Griffiths transversality. They're a very constrained class of maps. You get this sort of analytic map from this algebraic variety to this non-algebraic complex space. And in good cases, when you have a Torelli theorem, this map is actually injective. And even when you don't, you might have sort of infinitesimal Torelli theorems, which tell you this map is an immersion or something very close to an immersion. So you can really study your space via its image inside D mod GZ. So it contains a lot of moduli varieties, and even when your map is not injective, sort of the image in D mod GZ tells you everything the cohomology can tell you. It records a sort of cohomological part of your moduli. So one example, of course, is elliptic curves, as we've seen, but a more interesting example, if you haven't seen this before, is this example of Dwork. If you look at this family of quintic threefolds, you have an action by this group H. You can sort of resolve it, the quotient out, and then resolve it. and this gives you something with Hodge numbers 1, 1, 1, 1 from before, so it gives you a map to your V mod GZ. Okay, so you get curves, and also one thing I didn't put in the slides, but that's true, is that just like Shimura varieties, all these guys admit Hecke operators, because you can take your lattice, take any Hodge structure, just modify your lattice in some appropriate way, but there needs some sublattice and rescaling, and you will get more stuff. So it doesn't just contain curves or some algebraic varieties. The picture is that you have this non-algebraic complex analytic space, and inside there it's dense with sort of various curves of various complexity, various varieties, various complexities. You get this sort of tangled ball subvarieties. Okay, so I should mention the Hodge conjecture because it's the most famous thing associated with Hodge structures, and it's relevant to the story. So just very briefly, the Hodge conjecture tells you that if you have a smooth projective variety and you have a cycle inside it, something of codimension k, then you get a co-cycle. You get something, you can put it in cohomology as an H2K class. And it's in fact what's known as a Hodge vector. So it sits inside HKK, the middle piece. Now the Abel decomposition, the one concrete way to see this is if you restrict it to K form and you integrate along Y, and you want to get something not zero, well, the restriction better be not zero, so you better have exactly K holomorphic and K anti-holomorphic parts, because Y is a complex manifold. So you get this this Hodge vector, which of course we can totally abstract away, right? This condition makes sense for any Hodge structure whatsoever. You don't need to have any geometric input. This conjecture tells you that up to Q coefficients at least, all Hodge vectors are supposed to arise this way. So it's sort of the reason that it's hard, the same reason conjectures about rational points are hard. It's hard to make points, it's hard to make cycles. So where it's going to come from, in general, we don't know. Okay, so there's partial progress towards the Hodge conjecture. In some sense, the strongest sort of evidence towards it is the following. If you have a variation of Hodge structures on the base, which I haven't defined, you can just think of a smooth projective family sort of varying along the base. Then you can define the Hodge locus, which you can define in more precise ways, but I have this very sort of robust definition here, which is just look at those points on the base for which the fibro Hodge structure admits at least one Hodge vector. Right? You can ask for more specific things, but we can just focus on this. Then Catani, Deline, and Kaplan in 95 proved this wonderful theorem that this Hodge locus is a countable union of algebraic subvarieties of S in the general context of a variation of Hodge structures, but more specifically in this case of smooth projective families. And this is evidence towards the Hodge conjecture in that if it were false, the Hodge conjecture would have to be false because cycles come in algebraic families. So we know that these Hodge loci are just detecting the existence of some algebraic cycles. And if Hodge were true, it would have to be algebraic. Okay. All right. So let me talk about what we prove using this O-minimal machinery in this context. So everything stems from this theorem, joint with Ben Baker and Bruno Klingler, that says that this D mod GZ admits a definable analytic structure. So it already admits an analytic structure. So the key here is that it's a definable part. So that's easy, as I'll explain in a moment. Just putting a definable structure on a manifold is typically not a big deal. There's a million different ways you can do it. The important part is this next piece. It's that all period maps from algebraic varieties, which themselves have a definable structure, end up being definable with respect to the structure. Okay. So using this, we prove this conjecture of Griffiths in 69, which tells you that period images are algebraic. You have these period maps. You know, if they're injective, then of course the image is algebraic because it's injective. It's the image of an algebraic variety. But even in general, when it's not, if you're contracting something or the image is smaller dimension, you're still algebraic. So one way to think about this is the Hodge, the period map records these Hodge structures, which are these transcendental invariants. But this tells you that even though you're recording the transcendental invariants, the moduli space of those is still an algebraic. Okay, so more concretely, what does this state? To state it a little more formally. So given a period map, either stemming from a smooth projective family or not, to D mod GZ, you have this factorization as to D mod GZ through this algebraic variety Z, where Z is an algebraic variety. In fact, it's quasi-projective. Iota is a closed immersion, and this F is surjective in the scheme sense. So it's dominant, and the map achieves an injection. Okay, so sorry. Why would you expect this conjecture to be true? The motivation for it's actually pretty concrete, easy to understand. So Griffiths observed this first. So suppose you're in the best possible world where the image is smooth and compact. You have no degeneration, then you have no singularities. Then the argument's as follows. So D on it has a canonical 1-1 form, which is not a Kähler form, but its restriction to any Griffiths transverse map is Kähler. So you have this sort of weird property of period map. They have a lot of the structure that Hermitian symmetric spaces have if you restrict the Griffiths transverse directions. So in particular, this 1-1 form would have to be Kähler on your phi of S. Okay, but now you're projected by Kodaira and Bayer because you have an integral Kähler class. So Kodaira tells you that you're projected. So that's sort of the best possible case, which sort of explains why this theorem should be true in general. And it also explains, if I can go, sorry, my clicker is not, there we go. It also gives a hint of where this quasi-projectivity comes from, right? Because you sort of have this Kähler form, it's something that looks projective-ish. You can sort of make things work the right way. Okay. And there's some partial results. So Griffiths in the 70s, when he was working all this stuff out, proved this assuming just compactness of the image, any singularity is allowed. And Somese, using some sort of L2 cohomology methods, proved the case that you have only isolated singularities, that the image is algebraic in that case. Okay, so an interesting question that's still very much open is if you had a family that's defined over a number field like Q, you can look at the image algebraic variety. Is that variety defined over Q as well, or some number field? That's extremely open. It's related to the Hodge conjecture, in fact, something slightly weaker, the absolute Hodge conjecture. And the best way to think about this, I think, is you can imagine your S is just a curve parameterizing some family of varieties and therefore some family of Hodge structures. So what can happen is this curve can be injective except for 2 points glued together. So the image becomes some nodal curve. Okay, so why would 2 points glue together? Well, it's if the Hodge structures are the same. Now you want to know if you want some sort of number field structure, the arithmetic structure, you want to know that if that happens, if you have 2 points with the same fibril Hodge structure, they're defined over Q or something like that. Okay, this is, you can see, is related to some sort of absolute Hodgeness statement. And basically, in general, there's very little known. Okay, I shouldn't say that. There's important work known by Deli in Abelian variety has been generalized, but in this generality, not very little is known. Okay, so let's pay homage to this advertisement I gave in the last talk. I said that one of the motivations behind definable analytic sets is you can pull back definable analytic structure to algebraic varieties and get algebraic results. So let's make that happen here. So you can define the Hodge locus on V mod GZ. V mod GZ, the universal, the period domain is not Griffiths transverse. So a lot of things won't be true in V mod GZ, but you can still talk about all the relevant loci. So in this case, what is the Hodge locus? Is just saying you have some concrete vector, which you can fix one at a time, and you want that vector to be in the middle cohomology. So it'll be some actually algebraic variety, inside D check. And if you look at it inside D mod GZ, not just on D, it's some union, a countable union of orbits, where for each vector, you look at the stabilizer of that vector, you have some orbit, you descend it down mod GZ, you get some simple set like that. So claim, which I can't yet make precise because I haven't given you the definable structure on D mod GZ, the claim is once I give you that structure, then these orbits are going to be definable analytic. And given that they're relatively simple, hopefully you can believe me until we get there. And once you have this claim, you can reprove this theorem of Catani-Deligne-Kaplan immediately as a consequence of definable chow. Because the Hodge loci on S are the pullbacks under your period domain of the universal Hodge loci on your period space, D mod GZ. If your period maps are definable, which we claim they are, then the pullback of a definable analytic space is definable analytic on S. But now you're on an algebraic variety. And once you're an algebraic variety, definable analytic by Chow means algebraic. So these guys must be algebraic. And if you look at Catani, Deligne, and Kaplan's proof, it's a very clever proof, and it uses a careful study of degeneration. They sort of look near infinity, and they try to understand the sort of asymptotic behavior, and they get some control of it, such that they can apply regular Gaga, sort of the end game. They want to show that the closure of this Hodge loci, some compactification, is also analytic, and therefore by Gaga algebraic. And you can think of that as sort of, a shadow of what's happening here, which is some sort of much more, once you have the machinery of O-minimality, which is complicated to establish, it becomes easy to use. You can summarize all this stuff robustly just by saying things are definable in an O-minimal structure. Let me just do a time check because I don't have my phone with me because I forgot it somewhere. How much time do I have left? Oh, thank you. Awesome. No, 23 minutes. Okay. That's some sense. Thank you. Okay. All right. So let me give you the definable structure. So it's very familiar to what sort of happens for Shimura varieties, but sort of in that context, it happens. You prove that that's what ends up happening, whereas here you do it by fiat. That wasn't very clear. Let's just move on. So D itself, first of all, is semi-algebraic, right? D check is an algebraic variety, so that's semi-algebraic. And D is given by some real, algebraic positivity condition. So that's definable in real algebra. It's a semi-algebraic set. So D has a canonical definable structure. That's not complicated. Now, if we want to give a definable structure on D mod GZ, it's enough to pick a correct fundamental domain, a good fundamental domain F for the GZ action, and then just that maps bijectively to D mod GZ, and we declare that that's a definable structure. So when listening to last lecture, how I talked about given C star, you can lift to C and take the usual fundamental domain, or you can sort of take a tilted rectangle and you get many different definable structures. The choice of fundamental domain determines your definable structure. And in fact, you don't even have to be so careful. It's enough to give a fundamental set for GZ. So you don't have to be super careful. You get every point exactly once. Some kind of finiteness is sufficient. Okay, so what you use, which is familiar to anybody probably in this subject, is you use Siegel sets, rational Siegel sets for G of R, which I'm not going to recall, but I will recall the following sort of much more concrete interpretation you can give in terms of quadratic forms, which is really where Siegel sets stem from. So you can do the following thing. Given this kind of setup, you first pick a basis. You probably want it to be like Lagrangian align, but you can basically pick any basis for your lattice, any integral basis. Now, given a Hodge structure, I mentioned this before, I hinted this before, you can actually get a Hermitian form on your lattice tensor C, which is given in the following way. You just take your Q, you can define just the pairing Q, V, W bar, but that won't be positive. It will be positive or negative alternating on the different HPQ pieces, LPQ pieces, so you just fix it. You shift it by I to the P minus Q on the LPQ piece, and that gives you a positive form. So it's a minor change, but remember these LPQ pieces are sort of changing as your Hodge structure is varying. And so as you degenerate your Hodge structure, this becomes a more and more significant change, and your Hermitian form degenerates in some precise way, which was studied by Schmidt, who did a very careful analysis of this. His name will come up in a second. And then you just take your fundamental domain as you would for sort of the orthogonal group, or sorry, for the special linear group, if you were doing this, as just those Hodge structures where this basis that you chose is Minkowski reduced for the Hodge one. And what's Minkowski reduced? If you haven't seen it before, Minkowski reduced means you're as close to being orthogonal as possible, basically, right? So it's close to saying that all the angles are sort of close to 90, but that fails a bit if you have one short and one long vector, because then you can sort of change your long vector quite a bit till the angles start being affected. And so this is the correct notion. You insist that the inner products between different vectors are bounded by the Hodge norm of each of the different vectors. Okay, that's some analytic number theory, but you do this very concrete thing, and it gives you a fundamental domain, and you take that definable structure for D mod GZ. Okay, so now to justify this thing I said before, if you take H to be the stabilizer of vector, what do you have to do to show that the image in D mod GZ is definable? Well, you can imagine that you're looking at the H orbit. That's definable, and so the H orbit intersected with F is also going to be definable. But you're looking at the image in D mod GZ. So you really look at all the GZ translates of this H orbit, and the enemy is sort of the thing that could happen that would make it not definable is infinitely many of these translates intersect the fundamental domain, and so then that's bad. You can't have discrete infinities in definable sets. So you have to show that this intersection is actually finite. It only involves finitely many of these gammas. Luckily, we didn't have to do anything because this was already done by Borel and Hodge. And once you know that, you get a finite union. Therefore, these Hodge loci are definable for this definable structure. Okay. Okay. And then as far as period maps, I'm not going to go in detail on the proof, but I'll say the following. So first of all, Schmidt in 73 did a very careful analysis of the generations of Hodge structure as far as the Hodge norms are concerned and various other things. And he has this, everybody reads, including myself, everybody reads the paper up to sort of section 6 or 7. And then section 9 is where it gets really hard. And he has these this very intense theorem about precise generations of period maps, which if you unwind, actually shows exactly that period maps are definable in dimension 1. Basically equivalent to saying that if you degenerate along a disk, you get these sort of tight inequalities. He didn't phrase it this way, but that's what his theorem essentially amounts to. And even though we stated everything for algebraic varieties, the key case here to study is always polydisks. Everything is local. You don't really use the algebraic structure when studying generation. You just look at polydisks. So all we have to do is go from a dimension 1 generation to higher, and we basically find some sort of formal reduction to Schmidt's one-dimensional result. We get some sort of theorem which says that all the generations look a certain way, and then because you have all these sort of curves, these tori inside polydisks, and Schmidt tells you you're definable along all of those, you can show you're definable along the whole polydisk. Okay, so that's a very brief sketch, but that's the basic idea. Okay, so once you have the definable structure, I want to say a few words about how you actually show this Griffiths conjecture. Here images are algebraic. And what's nice about this is you actually completely forget the Hodge theory at this point. The Hodge theory has played its role. Now we work purely in this setting where you have a complex algebraic variety or even a scheme. You have any definable analytic space, and you take a proper definable map between them. So you have an algebraic thing mapping to, or the definabilization of an algebraic thing mapping to a definable analytic thing. And then the theorem says that in this case, the image is algebraic, just in this general setup. This is a theorem really in definable analytic geometry, not about Hodge theory. I guess Ben can't correct me because he's so far away, but my memory is we expect this to be true without the proper and can't prove it. Is that still true, Ben? More or less? Okay, I'm getting a more or less from Ben. So I think there's a question of whether this is true without the whether like the correct statement is true without the properness, which I think we expect to be, but we only needed this version. Okay, and I want to give an idea of the proof because, yes. Previous slide.
The combination of two parts of the image is final and it's closed.
No, it's a great question, and I'll tell you why. I think I understand the gist of your question. You're basically asking why don't you throw that and follow from some calculus. No, the point is that V legitimately is not algebraic. So V has lots of definable analytic subspaces that also aren't algebraic, named V itself, right? So somehow you have to send the algebraic structure from X. It's not going to come from V. That make sense? Great question. Other questions? The question was, is it known if it's a quasi-finite map and not proper? Yeah, I want to say yes. If it's quasi-finite, I want to say, I'm not sure, but I want to say yes. I have to think about it. Okay. So let me give an idea of the proof, because this proof is really what motivated definable Gaga in the first place so far. We're going to use definable Gaga as opposed to just definable Chaz. Because what are we trying to do? We're trying to show that some contraction, some image of an algebraic variety is algebraic. This was studied very carefully by Artin. So the first thing you do, I'm not going to go over this in detail, but using some Hilbert space argument, you can reduce to the following sort of key case where your map is an isomorphism away from some proper sublocus. You have a closed subvariety W of X, such that W gets contracted, and away from W, the map is an isomorphism. So that's some sort of standard Hilbert space argument. That's cool, but I'm not going to go over it. We're going to focus on this case. And then what Artin showed, he was working in the analytic category. This is in his paper where he was studying compact complex manifolds and algebraic spaces. He showed that to algebraize this map to give an algebraic structure to V, and I'm playing fast and loose here between definable and analytic, it's enough to algebraize the map on completions. So essentially, it's enough to algebraize the map on all infinitesimal thickenings. There's like epsilon more than that you have to do, but that's the central point. Okay. And so what you have to do is, well, by induction, you know that this W to Z, because there's smaller dimension, that in itself is algebraizable, by the theorem we're proving. What you have to do is show that the map on all thickenings, WK to ZK, for appropriate definitions of those thickenings, are also algebraic. So you have to find some sort of algebraic structure on the a priori analytic thickening. And the point of this is exactly some sort of definable deformation theory. What you can do is you can push forward the algebraic and therefore definable analytic structure on W, and you can show that Z, the structure on Z, is some sort of definable analytic thing inside there. There's something to prove that it really can be found inside there, and it's not something else, but you can do that. And once you have that, then you have the sort of bigger algebraic structure given by the push forward of the structure of W. And then by definable Gaga, anything inside there is also algebraic. Okay, that's some sort of sketch with obviously details to be filled in. But just to say it one more time, like that's the idea. How do you put an algebraic structure downstairs? You only have algebraic structures upstairs, so you got to find it from there. You find it definably analytically because you're in the definable analytic category. And since you're in something algebraic, Gaga tells you that everything stays algebraic. This is also why it's okay for us that we don't have an actual equivalence of categories between coherent sheaves, but we do have that the essential image is closed under subobjects. Basically tells you once you're in something algebraic, you can't ever leave the algebraic category again. I'm sorry? It doesn't mean anything. It's a vague thing meant to denote some intuition where really what you're doing is you're push forwarding some sort of structure sheaves on W, and you're finding it inside there. But you have to be a little careful that you don't sort of lose anything and you capture all of ZK. But the sort of the slightly more detailed, still slightly false outline of this is, yeah, you literally push forward the structure sheaves of the thickenings. You show the thing that's false unless you're careful, that the structure shift on Z sort of injects into that. And if you actually had that, you would be done by definable Gaga, because it would be, it's a definable coherent subsheaf of an algebraic sheaf, therefore it itself is algebraic. Other questions about this, or answerable questions about this very vague sketch? Okay.
Where does the Hilbert space come from?
Yeah, so that part is basically, you can imagine that your fibers are all positive dimensional. And in that case, you can look at those cycles, and you can just look at the Hilbert space of cycles like that inside X. Daniel's unhappy with me. Yeah. Sorry. Hilbert scheme. That was yeah. Yes, that's right. It means Hilbert scheme. Okay. Yeah, so if you replace it with Hilbert scheme, yeah, the question was, even if you replace Hilbert space with Hilbert scheme, what's going on. That's your question, correct? Oh, the fibers are algebraic, right? Because the fibers are in X, which is algebraic. So yeah, everything in X is algebraic by definable chow. Yeah. Okay, let me proceed. Yeah. So some corollaries for Griffiths. So we started this by I tried to motivate this talk with moduli. So what can you say about moduli? Well, assume you're any kind of M, which admits not just a Torelli, but a quasi-finite period map is enough. It's okay to have finite overlaps. So one example that we have in our paper is moduli of smooth, complete intersections in projective space. Then M is quasi-projective, which, by the way, I've said nothing about, right? I've only hinted that you use the scalar form somehow to get quasi-projectivity, but there's a whole argument there to get a quasi-projectivity. You get Borel algebraicity, which is kind of cool. So you have this for Hermitian symmetric spaces. Therefore, you have it for Shimura varieties. And you have it in this case as well for varieties that admit quasi-finite period maps. And I'll state it in this algebraic version. There's a polydisk version too, but I'm not going to say that. If you have any algebraic variety Z at all, sorry, this should be a Z, another typo. Then analytic maps from Z to M are all algebraic. Not definable analytic maps, that's always, but actual genuine analytic maps here are all algebraic. And this stems from some hyperbolicity of the period domain, sort of pulled back to M. And as a nice corollary, if you look at the analytification of M, it has an algebraic structure because it came from an algebraic thing, and that's the only algebraic structure. There are no other algebraic structures. Okay, I want to mention that there's sort of a much bigger world of definable analytic things one can study. So I want to single out this theorem by Baker and Moulin, I'm mispronouncing that maybe, that says concretely, if you take any algebraic variety, we talked about the period map, so Hodge structures. And if you think about it, Hodge structures are some sort of quotients of periods, right? The periods look at all integrals of all differential forms, and you only keep track of some kind of filtration. That's definable. Okay, but in fact, you don't have to do that. If you just look at all periods, those themselves are definable functions over the base, which is kind of nice. It's a very strong theorem. It's not strictly stronger than definability of period maps that I understand because of this quotient by G of Z thing that happens. But nonetheless, it's a huge collection of things that don't fit into Hodge theory that are definable. And you can actually talk about periods without having a family of varieties. All you really need is a local system by a Riemann-Hilbert argument. So given any complex local system, you can think of it as having sort of two structures. There's the flat structure, and there's the algebraic structure given by Riemann-Hilbert on its analytification. And if you pass back and forth between them, then the coefficients of that passing back and forth are sort of the periods of your local system. And so in that generality, Baker and Moulin show that those things are all definable, or said a different way, if you take the coherent sheaf associated to a local system, then that has an algebraic structure, if and only if your local system has norm one eigenvalues and infinity. There's some like regular singularities type condition here. And recently, as was talked about here, actually, Noah and Kurtz showed that it's if and only if. Sorry, so Baker and Mulaney showed the if part, and then the second F was recently also one. Okay, so finally, let me do an advertisement for the next talk. So here we talked about general period maps. So it turns out that the case I always think about, at least when I think about period maps, a sort of prototypical nice case is Shimura varieties, or AG in particular. Sort of a rich family where Hodge theory tells you everything. And one nice structure present in AG is that it has a natural compactification that's also given by Hodge theory, where the boundary pieces aren't Hodge structures, but there's some kind of degenerate Hodge structures coming from the type of family you're studying. And so you can construct that using this machinery for any period image, not coming from the Shimura structure. And one sort of cool thing that this gives is it gives a notion of modular forms without a lot of the extra arithmetic stuff, but nonetheless, I think it's fair to say have a reasonable notion of modular forms in this much more general framework, which we'll talk about next time. Thank you very much. Of which statement? Oh, in Griffiths, like in this kind of statement, is it clear where properness is used? Yeah, basically because we're push forwarding structure fields down, and yeah, I mean push forward doesn't work well if you're not proper. We expect that it's true without this condition. Yeah, which is different to say I expect to remove it. Sorry, I don't remember exactly what our thoughts on this were, but you have a thing to say or no?
You have a proper map.
Yeah.
Image was something.
And you take the image of a sub, like the Baily-Borel, then look at the map and complex. That's much included. Other than that.
But X is algebraic. X is algebraic though.
You start with a map, that's X minus C.
Yes.
Map the thing, which, but, wow, what you see.
Yes.
But like any image B, you like a Baily-Borel.
Yes, right. Right. So what Ben said, and maybe another way of saying about it is somehow the nice thing about I forget the person who asked the question. If you could, okay, great. Yes, sorry. One nice thing about the algebraic world is everything is compactifiable. So somehow you're not so far from being proper. The definable analytic world, that's not true, and somehow it makes it harder to go from non-proper things to proper things. But yeah, I don't know. I mean, there's something to rule out. It's not a pure form. I can't guarantee you we could do this like in a week or something. If we would.
Can you say something about how you use Schmidt to prove ongoing here?
Yes. So Schmidt, he proved the SL2 orbit theorem, which is not enough for definability of period maps. But then I'm forgetting the details, but he has a much stronger theorem in section 9, where he talks about the map from your polydisk to an SL2, to sort of the SL2 that occurs in the SL2 orbit theorem. And he proves, I forget how he states it, I'm sorry, but he proves like a very strong analytic control theorem, which exactly translates to your land in some fundamental Siegel set, some fundamental domain. So if you translate the theorem, it basically exactly gives you definability.
Ask at some point you said you were good, man. No, So at some point you mentioned that you have a curve reduction COI for proving definability of the period map. You assume that the basis.
Yes.
So is there a COI that has a curve COI? That means whenever we want
Like in general, you mean if you get a map from a poly? No, not in general. It's fairly specific. We end up getting essentially a power series expansion using there's like power series and some other, but very like log functions that show up. And four functions of that specific form, we prove a general theorem. That's it's enough for polydisks, but it's much more specific than just an arbitrary definable analytic map.
So you reduce dimension 1, and when you have your function here, do you have to know it for all delta star or just specific ones in specific directions?
I think we basically use for monomial delta star. So imagine like if your delta star is part of a C star of a GM, like a delta star to the K is part of a C star to the K, then you have like the monomial maps. Z goes to Z to the A, Z to the B, Z to the... Oh, okay, sorry. So what was your question about the dimension one?
Again, so you want that your
Yeah,
Dimension one.
yes,
In dimension one, it's needed to stuff.
yes,
And now I'm asking in the procedure of the reduction to dimension one.
yes.
Whether you have to consider really all, all curves in your initial place, careless.
Yeah, I think I was answering your question. So the S in general is a polydisk. That's what you reduced it. And in the polydisk, you look at like monomial curves. Yeah. Yes. Monomial curves are enough. I did my duty.
Very quickly, does the result you stated at the end about the definability of periods, does that have any immediate consequences to transcendence?
Right. So sort of. I mean, so we have a paper with Ben where we prove a very general transcendence theorem, like called the Anandri growth and peak period conjecture for function fields. So essentially, in some sense, determining all algebraic relations between anything you can build using integrals. There is a proof, the input into that is like a general X-Chanuel transcendence theorem, which you can prove using this kind of machinery, but there's also a proof using the recent differential Galois theoretic techniques of Guitag and the four authors in that paper. So there's two different inputs of like proving the X-Chanuel transcendence result, which you can translate into a transcendence result for arbitrary periods and iterated periods, sort of anything you can cook up using period functions.
If I want to put a Q structure or a reflex scale structure on the image, do I have to literally prove an absolute Hodge conjecture or just as an indication of why I think that?
So if you're willing to pass to the Stein factorization, then you don't have to prove anything. Then you're in pretty good shape because that rules out all these kind of coincidences happening. And it's kind of like an analog on the, so there's this like Zilberpink versus geometric Zilberpink stuff, likely intersections, where you can have like point exceptions and we don't know what to do with them, or you can have positive dimensional exceptions with geometry, and those we can handle. It's a similar story here. So in the general case, again, the main thing you have to rule out are just 2 points agreeing and understanding what goes on. So if you can do that, then you can actually do quite a lot, or if you pass the Stein factorization. But if you can't and you want the actual image, I think you're out of luck. I think you have to.
So there's also these theory additives. Are you willing to speculate about that?
Sure. I'll speculate. The hardest thing about, okay, so this is going to show my ignorance. In the classical Hodge theory case, you can actually embed sort of moduli into the theory economy. In the Hodge theory framework, in the Peterzil Hodge theory framework, my understanding is that's never actually true. You only sort of pick out the p-adic part. So you have to pass to some, this is really short from some like diamond type category or some sort of weirder category, which forgets some information. I would speculate that if you pass to that kind of category, then you have these kind of results once you can state them, which I have tried to do, but not too hard. We've been more time to understand the relevant structures. So I think the answer is basically yes, but you have to be careful what you say.
Okay, no more questions? Can we make it?